Good evening, I am Mr. Ish. Thank you for joining me. We're looking here at this hyperbolic sine function definition. Why are we doing that? Because it's one of the more important hyperbolics, especially with regards to the inverse hyperbolics. If you look here at the graph of a hyperbolic sine function, it's like that. Over its entire domain, it's an odd function. You can easily pass the horizontal line test. If you were to demonstrate the inverse of it would look something very much like this. Y equals x, imaginary line would very well establish itself right in between both of these. You have the basic function right there, you have the inverse function right over here. If f of x is equal to sine hx, which in terms of its definition is equal to this, then the inverse is equal to this right here, and I'm laying it out for you. And the definition is natural log x, all in an absolute value, and then x squared plus 1, close the absolute value. Look, everything here is with regards to inverse. That is inverse of that, that is the inverse of that. And you know, natural logs are the inverses of exponential functions. We have to demonstrate how you can come up with this, but we'll do it by two means. And we'll do it the more important way first, then we'll do like a backdoor approach utilizing integral and derivative approach secondly. If your function equals inverse hyperbolic, then x is equal to exactly what you're seeing right over here. You've taken the inverse onto the other side and it's become a non-inverse, or your original function. You can write this in terms of its definition. You'll have e to the y minus e to the minus y over 2, and you're seeing that I've implanted the y here in place of the definition of hyperbolic sine. Here it's inverse, but on this side it's become a regular hyperbolic sine is equal to x. Take the 2 on the other side, e to the y minus e to the minus y is equal to 2x. Bring all of these here in terms of these exponents into a more meaningful way. E to the y minus 1 over e to the y is equal to 2x. A common denominator over here would help. And you do this part right here, you'd have e to the 2y minus 1 is equal to 2x e to the y. I did the common denominator e to the y and I cross multiplied it and I attached it to the 2x. I want to convert everything here in regards to a quadratic style equation, and you're seeing it all come into form right over here. Let's do a substitution. U is equal to e to the y, and then this becomes u squared minus 2xu minus 1 equals 0. You have to bring in the quadratic formula, and you have here a is equal to 1 in terms of all the coefficients, b is equal to minus 2x, don't forget the x over here, and c is equal to minus 1. Bring the quadratic formula items into play. You'll have a 2x plus and minus b squared, which is a 4x squared, minus 4 times a times c all over 2. You know this is not going to be anything out of the ordinary. You'll have a 4x squared plus 4 over 2. If you were to isolate from that radical a 4, it could come out like this: 2x plus minus 2 root x squared plus 1 over 2. All of these 2's will cancel out, and you're left with here as u is equal to x plus minus root x squared plus 1. But I know u here is equal to e to the y. As you can see right over here, e to the y. E to the y is equal to that, then therefore y must equal to the natural log of all of this, x plus root x squared plus 1. We must get rid of that negative over there in case it would demonstrate or develop a negative, and you don't really want to do a negative of your log. You want to keep that to a positive value, and there you have it. Right over there is the definition of the inverse hyperbolic sine demonstrated for you. And that one is done. Let's show you the backdoor approach next. This unofficial approach, as I like to call it, the backdoor approach, starts as this. Look over here, you're doing the derivative of hyperbolic sine inverse. You know the derivative of this is 1 over root x squared plus 1. If you were to do the integral of this, you would end up back to the original function. Ideally you should. The only problem is when you do the integral of this, you don't end up back to the original function. And remember, we're doing this integral of that. You end up back to what is the representative definition of that, which is just as good as you ending up as that. And let's show you that. You're looking here at dx over root x squared plus 1. And you can bring in the trigonometric substitution technique here because it's ideal for this specific purpose. X here is equal to tan theta, because here a is equal to 1. Dx is equal to secant squared theta d theta. And you'll see when you take this back, you end up back to the definition of this, which is equal to you ending up as that. You have here secant squared theta d theta, and then here you'll have a tan squared theta plus 1. Remember, this is a square plus x squared type of trigonometric integral, so you can use this type of substitution. When you look here in the radical, you know tan squared theta plus 1 is a secant squared theta, but in the radical it becomes a secant theta. All of this simplifies with this cancelling out of that to a secant theta d theta, which you know is a natural log secant theta plus tan theta. We don't need to worry about the plus c because we're not done. When you come and look right over here, you know theta is equal to arc tan x over 1. You have to bring in everything here with regards to what you'll develop here from this triangle. x1 and then 1 plus x squared. When you're looking right over here, you're seeing the definition of these. Secant of this theta is going to be root 1 plus x squared. Plus, because of course you have that plus here. Then tan of this angle will be x. And then plus c. Right here is your definition again established. But you've basically gone from here back by means of the integral to your original function. This should represent your original function, but this right here is not representing this exactly in appearance, but it's representing its definition or what this is equal to in appearance. So this right here is equal to that. Anyhow, you can decide which of these approaches is better. I think the first original approach is a more accepted approach. This is like a bit more of an informal one, but I've shown you this definition here of inverse hyperbolic sine. Here's a definition, and you've seen it in the other way too. Well, that's it for this video. Thank you. Have a great day. Bye.